Okay, so the topic for today's class is a propositional logic. In class lecture, we introduce logical formulas. In this lecture, we're going to use logic to derive things. So today's highlights are the conditional statement and the arguments. Conditional statements or implications. If P, then Q. P is called the hypothesis, Q is called the conclusion. Some examples are, if your GPA is 4, then you will have full scholarship. So your chance at getting the full scholarship totally depends on your GPA. If your GPA is 4, then you have full scholarship. So here P is your GPA is 4, and Q, the statement Q is you will have full scholarship. So P is the hypothesis and Q is the conclusion. We can call hypothesis as antecedents and this is consequent. So when is the above sentence false? Let's just think about that. It is false when your GPA is 4, but you don't receive a full scholarship. Okay, so our claim here was if your GPA is 4, you get a full scholarship. If you get a GPA of 4 and you don't receive a full scholarship, then this above sentence is false. But what happens when your GPA isn't 4? Like if your GPA isn't 4, what happens then? We did not promise anything for this situation, right? You don't know if you have a scholarship or not. So in that case, this full sentence becomes true. This full sentence becomes true. Whatever the next portion is, you really don't care about it, because as you in your actual claim, you didn't say anything about what happens when you don't get a GPA of 4. You didn't say anything about it. So this whole sentence is logically true. I know this is very counterintuitive in a sense, but that's how the logic works. Okay, so this is not false if your GPA is below 4. So if your GPA is below 4, it is true irrespective of whether you receive full scholarship or not. Okay then. Another example is if there is a match of Bangladesh, then there is no class. Yeah. When is this false? When there is a match of Bangladesh and there is a class. Like this second portion doesn't happen. So there is a class. That's when this whole statement becomes false. And otherwise, otherwise, what is the other option? If there isn't a match of Bangladesh, you don't have to know the rest of it. Like there could be a class, there could not be a class. That doesn't matter. If there isn't a match of Bangladesh, this whole statement becomes true. Okay? So moving on. Logic operators. So if something, then another thing. If something, then another thing. Let's call this something P, then another thing is Q. So to write it mathematically, you can write it like this. P implies Q. This sign is equivalent to implies. Saying implies in literature, in English. So P implies Q. Whenever you have a logical statement like this, P implies Q, You can always find its logical states, by using every value of the variables. The variables are um, like the variables. It's not like variables. The statements are P and Q. These are the portions. You can try every possible combinations of these. You can say P is true, Q is true. Whenever P is true, Q is true, we know that P implies Q makes it true. If this whole statement is true. Whenever it's true and this is false, this is the only case when the whole statement becomes false. And it's like we've said before, if the hypothesis is false, as we didn't say anything about what happens when the hypothesis becomes false, this whole statement becomes true. Okay, so here we can see a valuable pattern. An implication is true provided P is false or Q is true. When does this become true? If P is true or Q is true. Okay, sorry. If P is false and Q is true, sorry. P is false or Q is true. You can write this like when it is true, like this implication can be written as not P or Q. Whenever P is false, look at it. Whenever P is false, the implication is true. Like our target statement is true. When P is false, this is true. When it is not false, like these two cases, when do we get a true answer? When Q is true. So in total, we can just observe these three things and write this whole situation as this: that P implies Q is logically equivalent to not P or Q. Okay, whenever P is false or Q is true. And there's only one case left when this becomes false. Can you say what this is? This is P and not Q. This is the only case when our implication is false. Yep, the convention is if you don't say anything wrong, then it is not false, thus true. Yep. Example implications. The most common type of statement in mathematics is the implication. Yes, it is. Consider the Pythagorean theorem. A square plus b squared equals c squared. Would you agree that this is the theorem? Or is this a statement? No, this is not a theorem. This is not a statement. The equation is true as long as A and B are the legs of a right triangle and C is the hypotenuse. Like this is not true for every triangle possible. And you like just by this statement only, you never know what are A, B, and C. So you have to first the if you have to first state that in this equation A and B are the legs of a right triangle and C is the hypotenuse. If that's the case, if these are the respected sides, then this happens. So if P, then Q. Let's make it a statement. Yep, can make it a statement. Suppose ABC represent the three sides of a triangle. If A and B are the legs of a right triangle with hypotenuse C, this is P implies this is Q. A square plus B square equals C square. Implications. This is a reasonable way to think about implications. Our claim is that the conclusion, the then part, is true. But on the assumption that the hypothesis, the if part is true, We make no claim about the conclusion in situations when the hypothesis is false. So this becomes true overall. This is why when the hypothesis is false, we don't say anything wrong, right? Like normally what did you start with? P implies Q. So if this becomes false, we didn't this becomes false, and whatever we say after that, it as it doesn't depend on this portion. Like we made a promise that whenever P is true, if P is true and Q is true, this whole thing is true. But you never said anything about when P is false. Like there was no basis. The premise here is wrong. You know, premise here is wrong. Premise here is false. So when the hypothesis is false, we don't say anything wrong. Like nothing contradicts our previous thinking. Our statement is not false and thus true. What do you mean if you say P implies Q is false? You mean whenever this, like they're asking you when this is false, when P is true and Q is false, that's the only case when this is false. Which of the following are true or false? An implication, if 1 equals 1, then most horses have 4 legs. Like we can see that this is true. So most horses must have 4 legs. Yep, like these two are true. Yep. This one's true, this is true. So the whole implication becomes true. And if 0 equals 1, we know that this is false. 1 equals 1 is obviously true. So as this portion is false, we don't really look at this side. We just only think about if something is, if false, then the whole statement becomes true. If 8 is a prime number, then the 7,624 digit of pi is an 8. Like you really don't know anything about this part, right? You really don't have to know. If you just look at after if, the condition is 8 is a prime number. Is 8 a prime number? No, it's not. So this is a false statement. So this whole thing becomes true. Even if you know that this portion is false, doesn't matter. This implication is true. Okay, if the 7,624 digit of a pi is an 8, then 2 plus 2 equals 4. In this case, you have to know this portion. You have to know this 7,624 digit, whether it's an 8. If it's an 8, if this is true, you don't know that. But there's a trick, there's a catch. You don't know what this is. Like it could be false or true. You don't know what this is. But suppose it's false. If this is false, this whole statement becomes true, right? Suppose this is true. This is true, and you can see that this is true, right? The second portion is true. The conclusion is true. The hypothesis is true. Then in that case also this becomes true. Like in both of these cases, this is true. So our answer is true. And this also follows our previous formula. Like our formula was not P or Q. Like whatever. Like if either Q is true or not P is true. P is false. Either this happens or this. In both of these cases, this whole statement becomes true. So sometimes by just looking at the conclusion, and if you see a conclusion which is true, like in this case also, the conclusion is true, this is immediately true. Or the premise or hypothesis is false. If you see the hypothesis as a false statement, this whole implication becomes true. Logical equivalence. Yep. if you see a question in the above form, there are usually three ways to deal with, like truth table. I think this is the best thing to do. Like you get every combination of P and Q, 0, 0, 0, 1, 1, 0, 1, 1. 1 being the true state and 0 being the false state. You could have used logical rules or intuition. Like this is a very sloppy approach to maths, so we'll skip this. Logical rules, yeah, we can do that, but logical rules sometimes fail us. Okay, like our hits, it's kind of tough just to wrap your head around why, when in an implication, if the premise is false, the condition is false, the statement is true overall. That's really tough to wrap your head around. So logical rules sometimes like may not follow our intuitions, and we could potentially make mistakes. On the other hand, truth tables are solid work. Okay, look at the false rows. Okay, if then what is our target? We want a compound statement equivalent to the left hand side. We need a compound statement. Okay, so look at the false rows, negate and take the end. This is the end product of sum, right? Look at the false row, or sum of product. This is a very famous thing in Boolean algebra to find the function from a truth table. Okay, look at the false row. Look at the false row. Negate and take the end. So how to make this one false? This is true. So what you can do is make it false. Like not P is gonna be false, obviously. And this is false beforehand. If you take a or here, 0 or 0, this is obviously 0 or 0 becomes 0. Yeah, this could be 0, but our best approach is 0 or 0. You don't take 0 or 0, you take 0 and 0. You go on. In this way, if it's like either one is not 0, it becomes immediately 1. So look at the false rows, negate and take the end. So this becomes not P, and this should be not P or Q. Okay, negate and take the end. Okay, so like I was doing before, I think I was doing I was going to the through the character approach. This is gonna be not P. Make this true or false, and then or Q. This makes this, right? Or you could have done it like take the P and not Q. So this becomes true. So true and true becomes true, and then take this. So by De Morgan's law, this already becomes this. Okay, by De Morgan's law, you can see this. See that by De Morgan's law, this not goes here and makes this and to or, not stays here, and not Q is basically Q. Okay, let's look at some examples. If you don't give me all your money, then I will kill you. So saying this, basically means this. Basically means this. Either give me all of your money, or I will kill you. Yeah. This is P, this is Q. So either you give me all your money, so you negate P. P was you don't give me all of money. So you give me all your money becomes not P. Or I kill you. I'll kill you. So this is Q. If you talk to her, then you can never talk to me. So this becomes, if you either you don't talk to her, either you don't talk to her, or you can never talk to me. Yep, that's right. If then as or. Okay, not P or Q. If you don't give me all your money, then I'll kill you. Either you give me all your money or I kill you. Yep, like I said before, this portion is easy. So, direct proofs or implications. To prove an implication, it is enough to assume P and from it deduce Q. You must explain why Q is true, but you get to assume P is true at first. So, to prove this statement, what you have to do that you assume that P is true. Like you assume it's true. You don't really have to prove it. Assume, and from that assumption, somehow try to prove Q. Okay, try to prove Q. And if you can prove Q, P implies Q becomes true. Direct proof is the easiest style of proof and has the advantage that such a proof often does a great job of explaining why the statement is true. Let's follow along. If two numbers A and B are even, then their sum A plus B is even. Okay, so to prove this, we just suppose that this is true. Suppose that number A and B, they're both even. You don't have to prove this, 2m and 2n. Okay, so these numbers are both even. And then try to prove from here to this, their sum is even. So let's just attempt to find out the sum. Sum is going to be A plus B. So 2n plus 2m, you take the 2 as a common. And this happens to be an even number, is an even number, 2. So this is proved, right? So this whole implication is true. Yeah, let me say equals 2j. Yeah, the sum is then a plus b. Yep. This means since k plus j is an integer, this means that a plus b is even. Yep. Assume p. So our normal approach here is assume p and then deduce q. Negation of if then. So if you negate it, what does it become? Let's try to solve this. Negation of P implies Q. So this is not a logical equivalent. What is the logical equivalent? Logical equivalent is not P or Q. So this becomes not P, which is P, and by De Morgan this interacts with this and makes this or into and Q. Yep, that's our answer. If P then Q. Okay, so here's the thing. If P, you're negating if P then Q. Our correct answer is this. Which one is the correct answer? None. Not any one of it is this. Obviously, this is not correct answer. Yeah, by De Morgan, they have also found this P and not Q. They're just proving it. So negation is negation of if then implication is P and not Q. If you eat an apple every day, then you have no toothache. So the negation would be you eat an apple every day and you have a toothache. Yeah, but you have a toothache. My computer is not working, and then if my computer is not working, then I cannot finish my homework. My computer, so its negation should be my computer is not working. Sorry, my computer is working. Oh, I'm sorry. My computer is not working, but I could finish my homework somehow. Yep. The contrapositive. This is very important. Always remember the contrapositive is logically equivalent to the implication. So, what is the contrapositive? The contrapositive is the statement if P implies Q, then not Q implies not P. This should be very easily understood by an example. If you are a student, CS first year student, then you're taking CSC 2110. If you're a CS first year student. Okay, so our contrapositive should be if you are not taking, this is Q, this is P. So not Q implies not P. This should be logically equivalent to saying this. So if you're not taking CSC 1, 2, 1, and 10, then you're definitely not a CS first year student. Like that's basic common sense. This is the contrapositive, which you can sense, like by your intuition, you can say that this is equal to the initial statement. The statement, if x squared is an even number, then x is an even number. So its contrapositive should be if x is an odd number, x squared is also an odd number. Like if x is a, to say it more clearly, if x is not an even number, then x squared is not an even number. Okay, so a conditional statement or an implication is logically equivalent to the contrapositive. Often it is easier to analyze the contrapositive. Suppose you're trying to prove a statement. This is the statement, you're trying to prove the implication, but as the implication and its contrapositive are logically equivalent, it's easier to analyze the contrapositive. It's easier to prove the contrapositive sometimes. In number theory, you'll often find that proving the contrapositive is easier. Like from this example, I think we can do it in the next slide. Okay, the slide after that, hopefully. A statement, if P, then Q. So if not Q, then not P. Okay, so proof using the truth table. Yeah, let's do it. We are going to see that this and this are basically the same. How do you write the truth table? You take P and Q, you write all of its combination as there are two states, P and Q, two variables, P and Q. So there are going to be total 2 to the power 2, 4 states. Like this can be in 2 states and this can be in 2 states. So 2 multiplied by 2 is 4. That's basic counting. So you write the normal state. Okay, so then you write not Q. You can negate the Q. T becomes F becomes T becomes F becomes T. And you then negate P, F, T, T. And after that, you try to do this. This implies this. So false and false becomes true immediately. And true implies false. This is false only, and this becomes true. So you can say that true, false, true, true. True, false, true, true. So this P implies Q, and this not Q implies not P is logically equivalent. Okay, what happened there? P implies Q is not P or Q. Not P or Q. This can be written as, like P implies Q. It can be written as not the first thing, the hypothesis, or Q. So this can be written as a logical statement like this, not Q or not P. This becomes not Q or P. Not Q or P. So this becomes Q or not P. So aren't these two the same? Yep, they're the same. Next thing, like what we have learned up until now, we have known the how an implication works. Implication is a statement. P implies Q. And when this implication is true and false, we have learned about it. And implications have, like, how to negate the implication. We have learned about that. Negation. We have found out that it's contrapositive, logical contrapositive, how to find it. Now we're talking is at the inverse. So the inverse of an implication P implies Q is the implication that not P implies not Q. Inverse is not logically equivalent to the original implication. That is, whether the inverse of an implication is true is independent of the truth of the implication. Okay, so these are logically two different things. This is the inverse. Like sometimes in real life, we take the inverse for granted. Like we take, you'll see. We see that, suppose if you are a person, you are a student. Okay, so sorry. If you're a person, you have to die. Let's suppose that. Let's say that if you're a person, if person, you have to die. If person, then D. Let's write it beautifully. If person, then D. Or then there is this, the inverse is if not a person, then you don't die. But is it true though? If you're not a person, you can be an animal, then you have to die. Or you can be a book or a computer, then you don't have to die. So there's ambiguity here, and this is not true. Like this and saying this are not exactly the same thing. So I guess you get it. The converse. The converse of an implication P implies Q is the implication Q implies P. So if P then Q, and you suddenly start saying if Q then P, if you start saying this, these two are obviously not going to be equal. The converse is equivalent. Like they're not equivalent. The converse is not logically equivalent to the original implication. That is, whether the converse of an implication is true is independent of the truth of the implication. Like it doesn't matter if the implication is true or not. The converse is independent of the truth of the implication. Okay, so normally, like in the previous slide, if you are a person, then you have to die. So you're basically saying in converse, like if you're conversing it, you're saying if you have to die, then you are a person. But are you? You could be an animal, right? You could be an animal. So this is obviously not the same as saying this. That's it. Converse is different. Yep. And now you could see like converse and inverse have this kind of have the same feel to it. Converse and inverse of a statement are logically equivalent to each other. Like you said, if you are a person, you have to die. What is the converse? If you have to die, you are a person. What is the inverse? If you are not a person, you don't have to die. Can you see how these two are equivalent? Because these two are contrapositive of each other. See, D implies P and not P implies D. So these two are contrapositive of each other. These two are logically equivalent, but these two are not logically equivalent to the mother statement, mother implication. Okay. So converse. Mathematics is overflowing with examples of true implication which have a false converse. And sometimes, like often, we take the converse and inverse for granted. Like I said, we take the truthness, the solidity of the converse as granted. Let's say it. If a number greater than 2 is prime, then that number is odd. So they're asking you, they're telling you that if the number greater than 2 is prime, if P, then O, that number is odd. Converse says that if a number greater than 2 is odd, then it is a prime. So if O, then P. But is this true though? If it's odd, then is it a prime? No, it's not, because 3 is a prime, 5 is a prime. These two are odd, but look at 9, for example. That's not a prime, right? So mathematics is overflowing with these examples where converse is not true. However, just because a number is odd doesn't mean it's prime. Yep. If a shape is a square, then it is a right rectangle. Like squares belong to the rectangles, right? Belongs to the set of the rectangles. So if a shape is a square, this is obviously going to be a rectangle. But are all rectangles square? No. So the converse is going to be like this. If a shape is a rectangle, then it is a square. That's not true at all. Like in both of these cases, you can see the set hierarchy, right? Like as S belongs to R, the set S belongs to R. You can say that if something is S, it's also R, but you can say the vice versa. You can say the reverse. Converse. Sometimes the converse of a true statement is also true, and that's just a coincidence. Okay, it's not necessary for a converse to be true if the statement is also true. But if that does happen, that says something. Okay, that's the topic of this slide. For example, the Pythagorean theorem has a true converse. Suppose ABC are the three sides of a triangle. If a square plus b squared equals c squared, then the triangle with sides AB and C is a right triangle. Okay, so normally we know what is the Pythagorean theorem, like what is the main implication. It was that if you have a triangle with sides AB and C in a right triangle, and it's a right triangle, then a square plus b square equals c square. But its converse is also true. Like I hope you have done the proof in your geometry class of proving the Pythagorean theorem and vice versa. I hope you did the vice versa. So you could prove that. Okay. So whenever you encounter an implication in mathematics, it is always reasonable to ask whether the converse is true. Because if that is true, then P implies Q is true and Q implies P is also true. So you could just write this. Q implies P is also true. P is technically then logically equivalent to Q. When both P implies Q and Q implies P are true, we say that P and Q are equivalent and we write P. This is also called the biconditional. Yep, this is called the biconditional. Okay, we'll come back to this soon. So true or false, if you draw any 9 playing cards from a regular deck, you'll have at least 3 cards, all of the same suit. Okay, so 9 playing cards from a regular deck. Draw 9. We call this draw 9. If D9, then 3 cards are same. Same suit. Okay, it's 3. 3 have the same suit. So this is basically saying that if you draw 9 playing cards from a regular deck, you'll have the same. So proving this can be a little hefty, but if you try to prove the contrapositive, what is that? If you what is the contrapositive? Like this is P and Q. P implies Q. The contrapositive becomes not Q implies not P. If you can prove that, this gets proven automatically. So what is not Q? If you don't have at least three cards, if at least three cards of the same suit, you can't have nine cards. If you, why am I writing this? We have the slides, I think. If you don't have at least three cards of the same suit, if you don't have at least three cards of the same suit, then you don't have nine cards. That does make sense, right? If you don't have at least three cards of the same suit, like what does that mean? You have at most two cards of the same suits, and there are four suits. So you have two cards, so this becomes eight cards at most. You can't have nine cards. This is proven immediately. So this is proven, so this is proven. Okay. Suppose I tell Rimpy that if she gets a 93% on her final, then she will get an A in the class. Assuming that what I said is true, what can you conclude in the following cases? Like we're told that this implication, if something, then another thing, this is true. So let's study the cases. Yep, we're said that P implies Q is true. Rimpy gets a 93% on her final. Okay, so just by looking at this, P implies Q is true. Okay, so if Rimpy gets 93% on her final, so if P is true, for this implication to be true, Q must be true. So she'll get an A in the class. Q must be true. Yep. So Rimpy gets an A. Rimpy gets an A in the class. Okay. So now we know about Q. So Q is true. Can you say anything about P though? Because as we've seen before, this whole implication becomes true if just this Q portion becomes true. And you want, like, this can be false or true, doesn't matter. If this Q is true, this whole thing is going to be true regardless. So you don't know anything about the state of P. Okay, the state of, if whether she has gotten 93% of her final, you don't know anything about it, so no conclusion. So cannot conclude anything. Rimpy does not get a 93% on her final. Okay, so if she does not get a 93% on her final, which means not P, for this whole statement to be true, this this can be either, like, you can be either true or false, right? Because this first premise is false. So we know this whole sentence becomes true, like the whole implication becomes true if just the hypothesis becomes false. So it doesn't matter what the Q is. So again, you cannot conclude anything about whether she will get an A in the class. You cannot conclude anything about Q. Cannot conclude anything. Okay. So Rimpy does not get. Next one is the Rimpy does not get an A in the class. Okay, so Rimpy does not get an A in the class. Okay, so this means not Q. Okay, not Q. For this to be true, this whole implication to be true, if you are given that not Q is true, then Q, I mean, not Q, which means just false. This is false. For this implication to be true, this can't be true. If this is true, if this is true, true implies false becomes false as a whole. So this must be false. P is false. So she does not get a 93% on her finals. And this is actually contrapositive, right? Not Q. P implies Q is logically equivalent to not Q implies not P. So we have the not Q portion here. It does not get an A in the class. So it must be that not P, which means she does not get a 93% in her finals. Okay. Implies if, only if. We know what implies is. Now we're going to learn two new keywords, if and only if. So implies, P implies Q, right? Saying this and saying that Q if P is logically equivalent, and P only if Q. These three are logically the same. Let's see. We can say that Q if P, i.e., if P, then Q. P implies Q can be written also as Q if P. Q if P. Here, remember that P is a sufficient condition for Q. If P, then Q. Like, is it sufficient though? If you know that this is true, okay, this is true. To know the state of Q, you have to know the state of obviously P. Like, if Q is true, then P is true. This is true, then this is false. Am I right? You have to know the states of P. So P is a sufficient condition for Q. Look at the true rows. When P is true, look at the true rows, like these rows, true rows. When P is true, what about Q? Q is also true, right? When P is true, like in the true rows, when P is true, Q is also true. So P is a sufficient condition for Q to make, like, P is sufficient to make Q true. Yep. Note that Q can still be true when P is not. It's sufficient. Sufficient, but not some doesn't say that it's necessary. Remember that. Yeah, it can make Q true, but doesn't mean that P's other values can't make Q true also. Doesn't mean that, but it can do that. It can make Q true. So we'll say that P is a sufficient condition for Q. Okay. So saying that P is a sufficient condition for Q is basically the same as saying Q if P. Okay, that's how they write it. This is the convention. Q if P, which means P is a sufficient condition for Q. Or jumping to the next portion, or you can say that P only if Q. So why do you say that? If not Q, then not P. If not Q, then not P. So in this case, contrapositively, if P then Q, right? Contrapositively, if P then Q, yeah. Q is a necessary condition for P. If you work hard, you'll succeed. If you work hard, you'll succeed. We're studying if and only if. If you work hard, you will succeed. So S implies R. You will succeed if you work hard. You can say it like this. S, this is R. You succeed. So S, you'll succeed come first. So R if B, sorry, R if S. You'll succeed only if you work hard. So this is only if. This is S. Sorry, R only if S. R if S means if S then R. Equivalently, S implies R. We also that S is a sufficient condition for R. R only if S means that if R then S. Okay, so this reverses. So equivalently, R implies S. We can say that S is a necessary condition for R. You'll succeed if and only if you work hard. If you combine these two, you'll succeed if and only if you work hard. After combining these two options, you get this. Okay, if and only if. This, this portion, if and only if, it can be written shortly as if. This basically means P and Q are logically equivalent. That is, P implies Q and Q implies R. Q implies P. Okay, let's do some options. Parent, if you don't clean your room, then you can't watch a DVD. Suppose this is C, and you can watch a DVD is D. The sentence is not C implies not D. This contrapositive is going to be D implies C, which should be also true. Like if you, but is it in real life? Yeah, math versus English. That's it. Is it? It's literally this is its literary meaning relevant in real life? We know that D implies C should be true. What is D implies C? What does D imply C? If you watch a DVD, you clean your room. Yeah, okay, that's logically true. In real life, it also means C implies D. If you clean your room, then you can watch DVD, right? You're hoping your parents will let you watch DVD if you clean your room because they have put you under an option that if you don't clean your room, you can't watch DVD. So the opposite must be true, right? This is in real life though. This does not mean that logically this is equivalent to this. In real life, it also means C implies D, but logically it doesn't. So if you're taking into account the real life's logics, C implies D and D implies C. So you could say C is equivalent to D, but is it? Not really. If a number x greater than 2 is an odd number, then x is not a prime number. Okay, so if is not an odd number means it's an even number. So even numbers are not a prime greater than 2. So the sentence says not odd implies not P. Of course, it does not mean odd implies P. Yep. So sentence says, yep, it does not mean that. Yep. The contrapositive is P implies O. If it's a prime, it's an odd. Yep. Being an odd number greater than 2. Okay, being an odd number greater than 2 is a necessary condition for this number to be prime, isn't it? Because if it's not odd, it can't be prime. So being an odd number greater than 2 is a necessary condition. Being a prime number is a sufficient condition for this number to be odd. So OFP. So OFP always brings sufficient one out, and P only if it's odd. Well, that's now that's a quite good example. But I think I remember it just by the logical thing. P only if O means O P implies O. And O if P is again P implies O. Necessary and sufficient condition. Yep. The if. True. Like there should have been P implies Q and Q implies P here. Okay. Let's just complete the chart. True. Okay, for P implies Q, true. Where is it false? Just here it's false. Otherwise true. And Q implies P. Where is it between true, false? This is gonna be false. True, 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 true. And whatever we're doing here is we're taking an and, so notice and operation. So true, true becomes true, true, false becomes false, false, true becomes false, true, true again becomes true. Okay, so this is our necessary and sufficient condition, the if table. As you can see, this is very similar to the XOR table, sorry, XOR table, right? Because this is XOR. It says, to be honest, XOR 1 1 gives you 1, 0 0 also gives you 1, 0 1 gives you 0, and 1 0 gives you 0. Sorry, it's not XOR, this is XNOR, I guess. XNOR. Hmm. Is a statement x is an even number if and only if x squared is an even number. True. If and only if. So to prove this, we're going to have to prove P implies Q first and then Q implies P first. And in these processes, sometimes you have to prove it's contrapositive because it's going to be easier. There are two steps. You have to prove this, you have to prove this, and whatever the statement is will be proved then. X is an even number if and only if x squared is an even number. So let's suppose that x being an even number, we call it statement P, and x squared is an even number, we call it statement Q. So we need to prove P if Q, if and only if Q. P implies Q and Q implies P. Let's do the first portion, P implies Q. X is even. Okay, so how to, like, lastly, what did you do? We did a direct proof, right? To prove P implies Q, we prove that we assume that P is true and we try to prove Q from it. So we are going to assume that x is an even number, so x equals 2k. So x squared is basically 4k squared, which is even. So from this you can prove this. This is Q. So it's proved. And B option is Q implies P. So if x squared is an even number, x is an even number. So you start by taking Q as a true thing. X squared is even, so you can write x squared equals 2k, so x equals root 2k. But after that, where do you go? Go toward 2k. You don't know anything, right? You can't write root 2, root 3 is an irrational number. This is pretty hard now. This is not the correct approach. You can also prove Q implies P by proving it's contrapositive, which is not P implies not Q. So not P implies not Q. X is not even. So X must be odd, right? Not P. Not P means X is an even number. So not P means X is not even. So X must be an odd number. So what is the contrapositive? Let's just say it again. Contrapositive is if x is an even number, then x squared is also an even number. Sorry, x is an even is not an even number, which means it's an odd number. X squared is also going to be an odd number. That's the contrapositive. If you prove it, you can prove that Q implies P. So x squared, you can see, which is not even, so which is odd. So contrapositive is proved. So to prove an if statement, you have to prove P implies Q and Q implies P separately. That's when you can prove this. Hypothesis and conclusion. If 1 equals negative 1, then I am the king of the world. Is this true? No, false. Then this whole implication is true. It doesn't matter if you're the king or not, the implication is true. It doesn't say anything about if you're the king or not. If computers are machines, which is true, then Mashraf is a cricket player. So then is Mashraf a cricket player? Mm, this is true. Yes, Mashraf is a cricket player, so this is true. If 2 plus 2 equals 5, which is false, you don't look at this. Okay, you don't look at this. 2 plus 2 equals 5, which is false. This already becomes true. But for meaningful statements, we formulate an implication when there is a relation between hypothesis and a conclusion. For meaningful statement, yeah, we need a relation in real life, but a hypothesis and conclusion in mathematics may not be related. Okay, may not be related. If 2 plus 2 equals 5, then Chandler is a girl. Yep, as 2 plus 2 equals 5 does not equal 5, which means this is false. This whole implication is true. You don't really care about it, whether Chandler is a girl or not. Okay, so the next thing. Conditional statement, I think we were done. The meaning of if and its logical forms, we have done it. Contrapositive is done. This is done. So next is the argument. We're done with conditional statements. If P something. If P, then Q. We're done with that portion. Then arguments. Okay, so argument form. An argument is a sequence of statements. Forms. All statement forms, but the final one are called assumptions and hypothesis or premises. Like in the previous example, conditional statement, you had one condition, if P, then Q. Now you're going to have more than one condition. That's called the argument. Okay, that's called the whole set is called the argument, and the more than one conditions you have, you're going to call it again hypothesis, assumption, or the premises. The final statement form is called the conclusion. Okay, so like in the implication, you knew that the implication is true, implication was false when the hypothesis was true, but the conclusion was false. So the final statement, but in this case, you have more than one hypothesis. So argument form is valid if assuming that all your hypothesis is true, like assuming that all of them are true, if you can derive the conclusion from it as true, then the whole argument form is valid. Okay, no matter what particular statements are substituted for the statement variables in its premises, whenever all assumptions are true, the conclusion is true. Whenever this happens, we can call that argument is valid. So argument is a sequence of statements, all statements, but the final one are called assumption or hypothesis. Okay. An argument is valid if its form is valid. So if today is Wednesday and yesterday is Tuesday, then yesterday is Tuesday. Like this implies this. If today is Wednesday, then yesterday is Tuesday. Suppose this is the first statement, and we say that this is true. We say that again, this is also true. Today is Wednesday. So what can you say? If this is Wednesday, today is Wednesday. If today is Wednesday, then yesterday is Tuesday. Yep, yesterday is Tuesday. So considering that these two are true, we can say this is true. And as all of these are true, this argument form is valid. This is valid because its form is valid. So there are many argument forms. We're gonna memorize important things from it. Okay, important ones from it. Modus ponens. If P, this argument form is of this form. You have a conditional statement at first, if P then Q, then they say the hypothesis is true, which means P. So the conclusion must be reached, right? So Q. If typhoon, then class cancelled. Typhoon, so class cancelled. So in this case, P, Q, you take all of its values. So P implies Q has these values. You say P, so to make this true, this should be true, right? These are the assumptions. The assumptions are that these are all true. Okay, so we're going to look at just this row. The assumptions, like, whenever you prove it, as I've normally said, you hold that these assumptions are true and try to prove the conclusion true from that. So if you can do that in one case, okay, I don't think there's a clash here. There's in true and true anywhere else. So this is the only case where the assumptions are all true, and I can see that the conclusion is true. So this is a valid form, modus ponens. Modus ponens is Latin meaning method of affirming. Modus tollens. So this is basically proving the contrapositive. Okay, this is the contrapositive one. If P, then Q, not Q, so P. If typhoon, then class cancelled. Class not cancelled, so it must mean that there's no typhoon. Again, we're gonna derive the logical truth table and these statements, and after that we're gonna look at when the assumptions are all true. Can you guess say it there? Here assumptions are all true. You can see it that the conclusions are true, right? So this argument form must be valid. So to prove if a argument form is valid or not, you just follow the truth tables for the different statements. You complete it and you then find which are the assumptions, and you try to find a match when every assumption is true, and then look at the conclusion. If all of the time every assumption is true, whenever the assumptions are true, the conclusions is also true, then you can say that this form of argument is valid. A modus tollens in Latin means method of denying. Okay, equivalence. So a student is trying to prove that proposition P, Q, and R are all true. She proceeds as follows. First, she proves three facts. P implies Q, Q implies R, and R implies P. Then she concludes, thus P, Q, and R and all true. Okay, so this is a writing form. Okay, this is a writing form. You take division like you did in division. You write the hypothesis up here, and this is her conclusion. You can also write it like this. Every question can be written like this. Okay, premises go up here in the numerator, almost a numerator, and the conclusion is written in the denominator. So this is her proposed argument, and we have to see that if her argument is valid. So let's do that. What I said, this is going to be a very big table. I think we've already done it. Is it valid? Okay. So you take every possible P, Q, and R values. Okay. So this is going to be like 2 for it, 2 for it. There are two states only, true and false, 2 for it and 2 for it. 2 to 2 becomes 8. So you have 8 rows. After that, you write these statements. You try to find the hypotheses and find their corresponding truth table. Yeah, already found. And after looking at these assumptions, we try to take those cases where all the assumptions are true. That's your only focus. So this is one and this is one. Are there anywhere else? No. In these two cases, now you try to find P and Q and R. This is true. This is false. No, this is not okay. So if all the assumptions are true, the conclusion isn't actually, it can be both, can be false. So it's not a valid argument. Assumptions are true but not the conclusion. So to prove an argument is not valid, we just need to find a counterexample, or look for all the examples and try to see if there exists a counterexample or not. Like, if it's a very exhaustive method, you have to try to see every case where all the assumptions are true. So these are valid arguments. If P, then Q. Uh, is it though? If P, then Q, Q, so P. No, I don't think this is going to be a valid argument. Let's see. P implies Q, Q. So whenever these assumptions are true, this is the case. P is true. Is it a valid argument though? No, because here also we have true, true, and this is a false statement. So we have found a counterexample. Let's see one example. If you're a fish, then you drink water. You drink water. So are you a fish? No. If P, then Q. Not P implies not Q. Let's do it. P, you take all the possible set of values for P and Q. You write P implies Q table, not P table. These are the assumptions. And you try to look at whenever the assumptions are all true. In these two cases, they're all true, but you can look at it. The conclusion is once false, then true. This is the counterexample. So this is not a valid argument. So this basically means if you're a fish and you drink water, you are not a fish, so you do not drink water. That's bogus. So they have given us exercises. Oh. Uh, we can do this by just, there are two statements, right? So P and Q. Let's do it here. P and Q. I don't think there are so much values in it. P, Q. So there are true, 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 false, false, true, false, false. Okay, so for P or Q, we're gonna write P or Q, P and Q, this. P or Q, P and Q, let's see, we have a Q naught. Do we have a P naught? No, let's just do it first, do these two first. P or Q. So it only becomes false when both of them are false. Other cases, these are true. And P and Q is true only when this is true and all of this is false. Okay, so let's look at this first one. Hypothesis is just P. Whenever it's true, like in these cases, is this true? P or Q. Is this true? Surprisingly, yes, they are all true. So this is a valid argument. Okay. P and Q. Okay. So this is the given one. We're going to look at this only through assumption. This line, this row. And is P. Yep. P is true. So this is also a valid argument. Oh, that's nice. P or Q. Okay. And not Q. We have to really go for it. Let's see. P or Q is true, true, true here and here. And Q not is true here only. Right? Yep. So we have to look at this row. And is it true? Yep, it's true. So this is also a valid thing. P or Q, not Q, so it means P. This is, I think, elimination. This is called elimination. We're gonna learn it about the last slide, I guess. This is also a valid argument. P, so P and Q. Okay, P is true in here and here. P and Q, no, this is false. I'm sorry, this is not a correct thing. P or Q. You look at P or Q and find the true. Oh my god, this is so many truths. See, there's one false conclusion, so this is not true at all. Okay, so P implies Q, Q implies R. You have to say this, right? P implies Q. I have to draw a new line. Okay, so whatever we are doing till now, let's just say it. P, oh, so this is valid. We did it right, I think. Not valid, okay. This one was also valid, I believe. This one was not valid. This one was valid. Yeah. See, this is such a big table. P, Q, and R. So P implies Q, Q implies R. So P implies R. So these two are their assumption. Uh, Assumptions are true here, here, and here. And in all of this are these one. Yep. All of this has one. So this is a valid assumption. Okay, P implies Q. Okay. So not P implies not Q. Okay, this. Not Q. So where are these true? True here. So this is valid, obviously valid. Not P implies not Q. So P implies Q. I don't think this is going to be valid because this is not, these are two are not logically equivalent, I don't think. P implies not Q, so 1 is 1, but look, 1 is 0, right? So this is not valid. This is obviously valid. This is the contrapositive. Valid arguments mean true conclusion, and true conclusion mean valid argument. Okay. So, if John Lennon was a rock star, then John Lennon had red hair. John Lennon was a rock star, so John Lennon had red hair. Red hair. This is modus ponens. Valid. But the conclusion is false because John Lennon actually had black hair. If New York is a big city, then New York has tall buildings. New York has tall buildings. So is New York a big city? I don't think this is a correct argument. Not valid. But the conclusion is true. So don't get your emotions mixed up with logic. With logic. 1 equals minus 1. So today is Tuesday. This hypothesis is never true, but we don't care if it's true in real life. We assume that this is true. We have make an assumption that all the hypothesis is true, and then try to deduct it. So this is valid, but the whole thing is not valid. Which form is this? P, so Q. You just say P, so Q. P and Q, we say that we look at this and see 0 and 1. Two different answers. There's a false case here. So this is not valid. Okay, so contradiction. Here C means contradiction, okay? So not P implies C. Okay. So P, not P. Look at this table. C is always 0. Okay, C is always 0. Like not P leads to 0, not P leads to a false case. And that's why P must be true. So not P implies Q. Okay, so whenever the hypothesis is true, the conclusion is true. If you show that the assumption that the statement P is false leads logically to a contradiction, then you can conclude that P is true. This is similar to the method of denying modus tollens. In a way that not P implies not true, which means false, and you can see that not true is just gonna be not really, not true, like true, yeah, true means P. Yep, modus tollens. Okay, knights and knave. This is my favorite type. Knights always tell the truth. Knaves always lie. So A says B is a knight. B says A and I are of opposite type. In these cases, these are the hypotheses, okay? So you know that knights always are going to tell the truth and knaves always lie. You know it. So think from, if you have like really little variables, really small number of variables, you should always brute force your way through. Suppose A is a knight and he's saying that B is a knight. So because A is a knight, he should always be telling the truth. So B must always be a knight, also be a knight. Now look at B. B should be a knight. Okay, B should be a knight. But B says A and I are of opposite types. So if B is a knight, why would he lie? They're not of the opposite type. They're currently of the same type. So this is a contradiction. So our previous assumption that A is a knight must be false. He is a knave. Okay, he's a knave. So whatever the knave is saying must be false, like they always lie. So B is not a knight, B is also a knave. That is our answer. Suppose A is a knight. Yep. Yep. Complex deduction. Nice one. We need all of this here. Oh, sorry. You saw the answer though. Let's just try to find my glasses. We're about to leave for Buet and in the morning and discover that you don't have your glasses. You know the following statements all are true. Like these are all are hypotheses. Reach a conclusion. Let's try to deduct like in the Sherlock Holmes. If I was reading the newspaper, yep, there are so many if, but you can't start from a if. Like to start, if you start from a if, you have to know the truth value of this first portion hypothesis. You don't know it, so let's just try to find normal statements. This is a normal statement. This is a normal statement. This should be a good starting point. I did not see my glasses at breakfast. Let's just try to find similar sentences related to it. Breakfast, where is the breakfast? Yeah. In A, we have breakfast. So if you say that this is true, I did not see my glasses at breakfast. If my glasses are on the dining table, then I saw that at the breakfast, right? So this implication should also be true. But if you did not see them at breakfast, you can say that my glasses are never on the dining table, right? So not on the dining table, you can say that because this implication is true. So we are applying modus tollens to A and D. Remember what was modus tollens? P implies Q, is the normal thing. P implies Q, P, so Q. That was modus ponens. We are talking about modus tollens, which is not Q implies not P. P, so Q. Sorry, the Q, P, so Q. Yep, isn't that? Yep. I didn't see them at the breakfast. Yeah, I did not see them in the breakfast. Sorry, I saw them in the breakfast is not P, but you did not see them as the breakfast is not P, so Q must be true. They're not on the table. Mm. So if they're not in the dining table, look at F. If I was reading on the newspaper in the dining room, then my glasses are on the dining table. Okay, so you know for sure that they are not on the dining table. So you were never reading the newspaper in the dining room, right? So you didn't use need newspaper in the dining room. Look at C now. If I no, don't look at C now. Look at B now. I was reading the newspaper in the living room, or I was reading the newspaper in the dining room. But like from previously seen, you did not read the newspaper in the dining room. So it must be that you are reading it in the living room. Now look at C. If I was reading the newspaper in the living room, then the glasses are on the coffee table. You know that this portion hypothesis is true, then the glasses must be on the coffee table. Yep, they must be. So the answer is the glasses are on the coffee table. So this is a complex deduction, and there must be a nice way to write it. Look, by applying A and D in modus tollens, you can say that your glasses are not on the. Yep, this is the modus tollens. I think I wrote it. P implies Q, so if they're not Q, so implies not P. This is like the contrapositive version of it. Yep. By if and one. Okay. By if and this one. What is if? If I was reading the newspaper in the dining room, then my glasses are on the dining table. Okay. I can say that they are not on the dining table. They're not on the dining table, so you are not reading the newspaper in the dining room. And by looking at this 2 and B, as there is a or here, so one of these must be true for this whole statement to be true. So if you're not in the dining room, you must be in the living room, right? So by B and 2 and elimination. So if you're in the living room now, then the glasses are on the coffee table. So by C and modus ponens, the glasses are on the coffee table. That's their normal way to write it. Okay, so some valid argument forms. This is very important. We learned about modus ponens. P implies Q, P, so Q. A modus tollens is P implies Q, not Q implies not P. This is basically the contrapositive version. Generalization. P, so P or Q. Q, so P or Q. Like, these are very basic. And you can go from P to or. Like one single variable to double variable. This is generalization. Specialization is P and Q, so P. P and Q, so Q. Okay, conjunction. P is true, Q is true, so P and Q both must be true. Okay. Elimination is P or Q. If not Q is true, then it must be P. Transitivity. P implies Q, Q implies R, so P implies R. Proof by division into cases. Okay, so P or Q? P implies R. Q implies R. So, because either P is true or Q is true, both of these cases lead to R, so R should be true. Contradiction rule is not if not P leads to contradiction or false thing, P must be true. These are all. So, a quick summary. Conditional statement. We learned about conditional statement and its logical forms. Learned about contrapositives, if only if. You learned about arguments where there are more than one conditional statement, more than one hypothesis. Definition of a valid argument, whenever the hypothesis, as I'm assuming your hypothesis is true, whenever the conclusion is also true, that's a valid argument. Sort of affirming, denying, and contradiction. Yep. More respondents, tolerance, and contradiction. So that's it. That's basically your class. Real herself for the next class. The sentence below is false. The sentence above is true. Like, what is this? The sentence, if you try to solve it like the knight and the knave's problem, you start by saying that this first sentence, let's just suppose the first sentence is true. So the sentence below should be false. And when you go to, like, when you try to assume that, make an assumption that the second sentence is false, must be false. But what this sentence is saying, the sentence above is true. So there's a contradiction, right? You reached a contradiction. So if you start to grow from here to here to there, you'll also reach a contradiction. So if you reach contradiction both ways, this is a paradox.